Hey everyone, welcome to this explainer. I invite you to just take a breath, relax, and settle in. Today, we're going to slow things down a bit. We're going to explore the quiet, almost totally invisible chemistry that powers, well, practically every aspect of your daily life. It's this fascinating, gentle rhythm of stored energy. And honestly, by the time we finish up here, you're going to look at your everyday electronics in a completely different light.
So I want to ask you something. What is silently powering your world right this exact second? Just take a quick pause and look at the device you're using to watch or listen to this explainer. Chances are you're not tethered to a wall outlet, right? You're running on invisible energy, neatly packaged into a sleek little rectangle.
It's kind of wild when you really think about it. This quiet electrochemical engineering is literally what gives us our modern mobility. From that smartphone glowing in the palm of your hand, to the laptops we use for late-night studying, all the way to electric vehicles silently gliding down our streets. Absolutely none of this personal freedom would be possible without a super reliable, portable source of electrochemical energy. It is, without a doubt, the silent enabler of our modern world.
To truly appreciate how this works, we kind of need to strip away all the complex jargon for a second and just look at the absolute basics. What actually is a battery? At its core, a battery is just an electrochemical device. Its one and only job is to convert stored chemical energy directly into electrical energy. That's it. It's this beautifully simple converter, taking potential energy and turning it into the kinetic spark that lights up a screen.
Okay, so picture this architecture as a highly controlled, closed-off little environment. You've got the anode, that's the negative side where electrons want to break free. Then you have the cathode, their positive destination. Sandwiched right between them is the electrolyte, which is basically a chemical pathway that allows specific particles, called ions, to migrate across. And finally, a separator keeps the two sides safely apart so they don't short-circuit. It's a completely sealed system, which, is very different from, say, a Zinc-Air battery. Those actually breathe oxygen directly from the outside air to function. But in our system here, everything is neatly contained.
When we bring all these components to life in a modern context, we get the absolute star of our explainer today, the lithium-ion cell. It's a secondary, rechargeable battery that has entirely revolutionized how we store energy. Notice how it has those distinct layers with the separator sitting right in the middle, perfectly organizing the space.
Let's zoom in a little closer on those two main rooms we just talked about, but specifically for the lithium-ion battery. The positive electrode, our cathode, is typically built from layers of a chemical compound called lithium cobalt oxide. Think of this as the cozy, comfortable starting home for our ions. Over on the other side, the negative electrode, our anode, is made from layers of porous carbon, usually graphite. It acts as a sponge. Actually, scratch that. It's more like a porous matrix, ready to absorb and store the ions in a process called intercalation. It's this exact, specific combination of materials that gives the lithium-ion battery its incredible lightweight efficiency.
Now, I absolutely love this next part. There's a wonderfully surprising fact hidden in all this chemistry. Despite the name lithium-ion, these rechargeable cells do not actually contain any solid metallic lithium. No way, right? Because metallic lithium gets highly reactive in aqueous solutions. Instead, this entire system relies purely on the gentle movement of lithium ions, which, remember, are just atoms that have lost an electron, floating back and forth between the layers.
So, what does this all mean? Well, it creates what we can think of as the rhythm of the battery. It's a peaceful, back and forth, rocking chair kind of motion. When your device is plugged into the wall, we call that charging. We're literally forcing energy in, pushing those lithium ions away from their comfortable home. But the second you unplug and start using the device, discharging, those ions spontaneously just want to migrate back. And it's that relaxed, natural return journey that releases the electrical energy you use.
It's literally a microscopic dance. Those tiny positive lithium ions are in a constant ebb and flow, using that gel polymer electrolyte in the middle as a bridge between the electrodes. They slip neatly into the layers of graphite on one side and then seamlessly slide right back into the lithium cobalt oxide on the other. It's beautiful, really.
Let's break down that charging dance real quick. When you plug your charger into the wall, that external power acts like a gentle push. It forces electrons out of the positive electrode and pushes them through the wires to the negative side. To keep everything balanced, our tiny lithium ions have to follow suit. They leave their home in the lithium metal oxide, travel carefully across that polymer gel, pass through the separator, and finally settle into the porous carbon layers. They just pack themselves in there, holding on to all that potential energy. And then comes the discharging dance, the relaxing return trip. The moment you turn on your phone or hit the accelerator on an EV, the system is allowed to relax. The lithium ions spontaneously migrate back to their original home. Because they're moving, the electrons are forced to flow back through the external circuit, the wiring of your device, to balance the charge. That exact flow of electrons, that is the electricity that brings your screen to life. It's literally just nature trying to find balance again.
So, zooming out from that microscopic level for a sec, why does this matter in the real world? Well, because lithium-ion batteries have such high voltage, high energy density, and zero memory effect, they are literally everywhere. While something like a Zinc-Air battery is fantastic for applications like hearing aids because it provides this steady, low power from a tiny, air-breathing package, lithium-ion is the heavy lifter. It powers our phones and laptops. It powers critical medical devices. It is the driving force behind high-performance electric vehicles. It captures kinetic energy through regenerative braking and can even push power back into the electrical grid during peak demand to stabilize our cities. The engineering chemistry literature really hits the nail on the head here, stating, "The versatility and efficiency of lithium-ion batteries make them a cornerstone of modern electric vehicle technology." Just think about that for a second. This simple, microscopic back-and-forth flow of ions is, for sure, driving the global automotive industry toward a cleaner, far more sustainable future. As we wrap up this explainer, I just want to offer you one simple, low-pressure takeaway. You don't need to memorize the chemical equations or the exact materials. Just remember this. Every single time you plug in your phone, your laptop, or your car, you aren't just filling a tank. You are simply giving billions of tiny, invisible ions the energy they need to make a little commute across a microscopic space. It's just this gentle, continuous rhythm of tension and release happening right there in the palm of your hand. Next time you plug your device into the wall, I really hope you take a second to picture that quiet dance of the ions inside. It's a pretty peaceful thought, and it definitely gives you a whole new appreciation for the incredible science keeping our modern world ticking. Thanks so much for hanging out with me for this explainer, and keep exploring the amazing world around you.